Once we've determined our normal requirements and our security requirements, we must design the software and we must implement it. Defects could be introduced in either of these two activities. Defects in the design are called flaws, and defects in the implementation are called bugs. The goal of the design phase from a security perspective is to avoid flaws. Now, while a lot of security-related focus is on implementation bugs like buffer overruns, flaws are equally important. According to security guru Gary McGraw in his book Software Security, roughly half of security-relevant software defects are flaws, not bugs. So getting the design right is extremely important. What I've just said may make it seem like there is a crisp distinction between the design and implementation of a piece of software, but that's not entirely true. Rather, design and implementation occur at many different levels of abstraction. For example, at the highest level, we are concerned about a system's main actors. These might be elements like a web server, a database management system, and a client's browser, each running in its own process and communicating with one another. The choice of programming language to use or framework is also a fairly high-level design decision. At the next level down, we're concerned with the internal design of each of these actors. A web server is going to consist of many different functions and objects. How should these be organized, and how do they interact? This is a question of design. At the lowest level, we must decide how to represent data structures, how to implement a piece of functionality, for example with one method or three, and so on. When someone speaks generically about a software system's design, he may be speaking about any or all of these levels. When speaking about its implementation, he might also be thinking about the lower level, or maybe the lower two. However, we believe there is design happening at the lower levels, and the choices made there affect security. So when speaking about design, we mean all three levels, and which in particular should be clear from context.
The software design process aims to produce a software architecture according to good principles and rules. This is an iterative process. We first put down our initial design, and then we perform a risk-based analysis of that design. As a result, we may determine that the design needs to be improved. And so we apply our principles and rules and then improve it until we are satisfied. A principle is a high-level design goal with many possible manifestations, while a rule is a specific practice that is consonant with sound design principles. Now, the difference between these two can be fuzzy, just as the difference between design and implementation is fuzzy. For example, there is often a principle underlying specific practices. Principles may also sometimes overlap. The software design phase tends to focus on principles for avoiding flaws, and less on rules, which are more part of the implementation phase. We can group our set of software design principles into three categories. The first category is prevention. These sorts of principles aim to eliminate software defects entirely. For example, the Heartbleed bug would have been prevented by using a type-safe language like Java, which prevents outright buffer overflows. The second category of principle is mitigation. These principles aim to reduce the harm from exploitation of unknown defects. That is, we can assume that some defects will escape our elimination during the implementation phase, but if we design our software in the right way, we may make it harder for an adversary to exploit these defects in a way that's profitable to him. As an example, we could run each browser tab in a separate process, so that exploitation of one tab does not yield access to data that is stored in another tab because it is isolated by the process mechanism. The third category of principle is detection and recovery. The idea here is to identify and understand an attack, potentially undoing its damage if we're able to recover. As an example, we can perform monitoring of the execution of our program to try to decide whether an attack has taken place or might be in the process of taking place, and we could perform snapshotting of various stages of our software's execution in order to revert to a snapshot if we discover later that an attack has corrupted our system.
So now, without further ado, here are the core principles we have identified for constructing secure software. First, favor simplicity, and in particular, use fail-safe defaults and do not expect expert users. Next, trust with reluctance by employing a small trusted computing base and granting a component the least privilege it needs to get its work done. Ensuring least privilege may involve promoting privacy and compartmentalizing components. Next, defend in depth, avoiding reliance on only one kind of defense. The word depth also means depth of attention by employing community resources such as hardened code and vetted designs. Finally, monitor and trace to be able to detect and diagnose breaches. Our principles are strongly influenced by a set of principles put forth way back in 1975 by Jerome Salzer and Michael Schroeder in their paper, Protection of Information in Computer Systems. It's amazing to see how well these principles have kept up, despite systems, languages, applications, all being very different today compared to what they were in 1975. Here are the principles suggested in Section 1 of the Salzer and Schroeder paper, where those in green are identified as principles and those in blue were considered by the authors as relevant but imperfect in their application to computer systems. Comparing our principles to the classic ones, there is substantial overlap. Some of the classic principles have been regrouped or renamed, and some expanded in scope. We have added monitoring in support of forensics because successful attacks are inevitable, and you need a way to diagnose and improve on past failures. Salzer and Schroeder may have been also concerned about this, but in their paper were more focused on prevention. Finally, I have dropped their principle of complete mediation, which states simply that all security-relevant actions must be mediated if policies on them are to be enforced. I don't think of this as a design principle because all designs that lack it are insecure by definition. In that sense, it is a requirement, not a principle. By comparison, a design could lack all of the other principles and still be secure, but achieving security with such a design would be very difficult and would be very hard to maintain. Okay, next we will dig into these different design principles organized by category and starting with favor simplicity.